All right, let's dive in. You sent over a ton of stuff about neural networks and deep learning, articles, videos, even some glossary terms.
Yeah.
So clearly this is something you really want to get a handle on.
It's a hot topic for sure.
It is, and it's changing so fast.
Yeah.
Which I think is part of the appeal and also the challenge.
Right, right. And it's interesting because your curiosity here really does mirror a broader trend. Neural networks had a bit of some experts call it a winter for a while, but now they're really back in a big way.
Exactly. So for this deep dive, consider us your translators. We're going to take all this complex material and break it down into the stuff that really matters.
Yeah.
We're going to go beyond just basic definitions and try to understand the real impact of this tech.
I think the key is to not just learn the what, but the why.
Yeah.
Why are neural networks so important now? Why should we care about things like perceptrons or backpropagation? We'll explore all of that.
Love it. So let's start with something I think a lot of people wonder what exactly is a neural network. It's one of those buzzwords you hear everywhere.
Right.
But what's the real deal?
Well, think of it like this. Imagine a network of tiny interconnected units, almost like a miniature brain.
Okay.
Each unit, or neuron, processes information it receives from others, and collectively, they can learn to perform complex tasks.
Okay, that's helpful. But how does this relate to something like, say, Google's search algorithm or self-driving cars? I mean, those feel like huge leaps from a miniature brain.
You're right, the scale is definitely different, but the principles are surprisingly similar. In Google search, for example, neural networks help understand the intent behind your search terms,
Okay.
and then they match them with the most relevant websites. It's all about recognizing patterns and making connections, just on a massive scale.
So it's like each of these tiny units is contributing a little bit of knowledge, and together they build up this incredible understanding.
Yeah,
That's pretty wild.
it is.
But let's zoom in a bit. You mentioned these neurons processing information. How does that actually happen?
So each neuron receives input signals from other neurons, and these signals have different weights attached to them, kind of like voting power.
Okay.
So stronger signals with higher weights have more influence on the neuron's decision.
Okay, so the weights determine how much each input matters. Then what?
The neuron takes all those weighted inputs, does a little math on them, and decides whether to fire, meaning send out its own signal to other neurons.
Okay.
This process, repeated across layers and layers of neurons, is how the network makes sense of data.
All right, I'm starting to get the picture here.
Yes.
We have these interconnected neurons passing signals, voting on what the output should be. But how does the network learn in the first place? How does it know which weights to assign to different inputs?
That's where training comes in. And this involves one of the most important concepts in neural networks, backpropagation. Think of it like this. The network makes a guess, compares it to the correct answer, and then adjusts those weights based on how wrong it was.
So it's learning from its mistakes, kind of like we do in real life. You make a mistake, you adjust your approach, you try again.
Exactly. The more data the network is exposed to, the more it refines those weights, becoming more accurate over time.
Okay.
This is how it learns to, say, distinguish between a cat and a dog in an image, or translate a sentence from English to Spanish.
This backpropagation thing is clearly key here, but it sounds kind of complicated. Can we maybe unpack that a little bit more?
It is complex, but the core idea is surprisingly intuitive. Imagine you're learning to ride a bike.
Okay.
At first you wobble a lot, maybe you even fall. But each time, you adjust your balance, how you steer, how you pedal. Backpropagation is the algorithm that helps the neural network make those adjustments, but instead of your body, it's tweaking those weights.
I see. So the network is constantly making tiny adjustments, getting better with each attempt. It's like this self-correcting system driven by data.
That's a great way to put it. And this ability to learn from data is what makes neural networks so powerful and adaptable. They can be applied to a wide range of tasks, from recognizing images, to generating text, to even predicting stock prices.
Okay, so we've covered the basics of how these networks work.
Yeah.
But there's a whole historical side to the story too, right? From what I've read, it wasn't always smooth sailing for neural networks.
You're absolutely right. Neural networks have had a fascinating and somewhat turbulent history. In fact, they went through a period known as the AI winter, where research and funding dried up.
Really? Why did that happen? I mean, the concept seems so promising, even from those early days.
Well, the early neural networks, like the perceptron, were quite limited in what they could do. They could only solve certain types of problems, and they really struggled with more complex tasks.
So it was a case of the hype getting ahead of the reality. People expected too much too soon.
That's part of it. Also, the computational power needed to train larger, more complex networks simply wasn't available back then.
So what changed? How did neural networks come back from this winter and become this powerhouse technology they are today?
A confluence of factors played a role. New algorithms, like backpropagation, were developed that made it possible to train multi-layered networks.
Uh-huh.
And computing power increased exponentially.
I've also heard that the video game industry played a surprising role in this resurgence. Something about those fancy graphics cards.
You're on the right track. The demand for realistic graphics in video games led to the development of GPUs, graphics processing units.
Okay.
And these GPUs turned out to be incredibly well suited for the kind of parallel processing that neural networks require.
So gamers inadvertently helped fuel the AI revolution.
Yeah.
That's kind of amazing. It shows how seemingly unrelated fields can have these unexpected connections.
Absolutely. It's a great example of how innovation in one area can have ripple effects across other domains. And speaking of innovation, this resurgence led to what we now call deep learning.
Ugh.
Deep learning. That's
Yep.
another one of those buzzwords you hear everywhere.
Yeah.
So is deep learning just a fancy way of saying neural networks with more layers?
Essentially, yes. Deep refers to the number of hidden layers in the network. The more layers, the more complex the patterns the network can learn.
Right.
And with the boost from faster computers and better algorithms, researchers could finally build and train these deeper, more powerful networks.
Okay, that makes sense. So more layers mean more complexity, which means more learning power. It's like leveling up in a video game. But I'm still curious about those hidden layers.
Yeah.
What exactly is happening in there? How do they contribute to the learning process?
Imagine you're trying to recognize a friend's face in a crowd. Your brain doesn't just process the whole image at once, right?
Oh, of course not.
It breaks it down into features.
Mm.
Their eyes, their nose, their hair. Hidden layers do something similar.
So each hidden layer is looking for specific features and then passing that information on to the next layer. Exactly. Early layers might detect simple edges and shapes, while later layers might identify more complex features like a whole face or even an emotional expression.
That's incredible. It's like these hidden layers are building up a more and more sophisticated understanding of the image as they go. But how do they know which features to look for?
That's where the magic of backpropagation comes in again.
Oh.
The network starts with random connections and weights, but as it's exposed to more data, those weights are adjusted to emphasize the features that are most helpful for making accurate predictions.
Okay, so the hidden layers are essentially evolving, becoming more specialized as the network learns. This is mind-blowing. I'm starting to see why deep learning has had such a huge impact on so many fields.
It is. It's a truly transformative technology, and we've only just begun to explore its full potential. But before we dive into specific applications, I think it's important to understand the different types of neural networks that have been developed.
Okay.
Each type has its own strengths and weaknesses, and they're suited to different kinds of tasks.
Ooh, that sounds interesting. I'm ready for a deeper dive into the world of neural network architectures. What's next on our journey?
Welcome back. Ready to explore some different neural network architectures?
Absolutely. We've laid a solid foundation, and now I'm eager to see how these different types of networks, specialize in tackling various problems. It's like meeting different members of a talented family.
That's a great analogy. Let's start with one that's become incredibly influential in recent years, the transformer. It's really revolutionized the way we handle language.
Oh, yeah, transformers. I've heard so much about them, especially in the context of those mind-blowing language models like GPT-3 that seem to write almost like humans. What's the secret sauce behind them?
It all comes down to a clever mechanism called self-attention. Remember how we talked about neurons assigning weights to different inputs?
Uh-huh.
Well, self-attention takes that to a whole new level.
Okay, do tell. How does it work?
Imagine you're reading a sentence, "The cat sat on the mat." Now, to truly understand the meaning, you can't just look at each word in isolation.
Right.
You need to consider the context, the relationships between words.
Right, like cat and sat clearly go together, and mat is the thing being sat upon.
Exactly. Self-attention allows the network to do this. It figures out which words are most relevant to each other, even if they're far apart in the sentence.
Okay.
It's like each word is looking at all the others and saying, "Hey, you're important for understanding me."
So it's like building a dynamic map of the sentence, where the connections between words are constantly shifting based on their relevance to each other. That's pretty sophisticated.
It is. And the beauty of transformers is that they can handle much longer sequences of text than previous models.
Uh-huh.
They can remember information from earlier parts of a paragraph or even a whole document, which makes them incredibly powerful for tasks like translation or summarization.
Okay, let's take a specific example. Say I'm using Google Translate to understand a news article in another language. How would a transformer approach that?
It would first use its encoder to analyze the original text, building up that rich representation we talked about, capturing all those nuanced connections between words.
Right.
Then the decoder part of the network uses that information to generate the translation, paying attention to both the original meaning, the grammar, and style of the target language.
So it's not just about swapping words, it's about truly understanding the meaning and then recreating it in a whole new language. No wonder translation tools have gotten so much better recently.
Got it. Transformers are also great for things like writing different kinds of creative content or summarizing large amounts of text. They're even being used to help programmers write code.
It's kind of mind-boggling how versatile they are. But let's shift gears a bit. I know there are other types of neural networks, each with its own specialty. What else is out there?
Another prominent family is the convolutional neural network, or CNN.
Okay.
These are the masters of image recognition.
Ugh. CNNs. I've heard about those, especially in the context of things like facial recognition or self-driving cars. But images seem so different from text. How do CNNs approach them?
It's all about recognizing patterns. But instead of words, they're looking for visual patterns. Imagine you're looking at a picture of a cat.
Oh, okay.
Your brain doesn't see it as one big blob of pixels, right?
Of course not. I see ears, whiskers, those adorable eyes.
Exactly. CNNs work similarly. They use filters that scan the image, looking for specific features, edges, corners, textures.
Uh-huh.
These features are then combined in layers, building up a more and more complex understanding of what's in the picture.
So it's like those hidden layers we talked about before, but instead of abstract concepts, they're focusing on visual elements?
That's a great way to put it. Early layers might detect simple lines or curves, while later layers might recognize entire objects, like a cat's face.
Okay, that's making more sense now. But how do they actually learn to do this? Do they also use backpropagation?
They do. The process is very similar to what we discussed earlier. The CNN is fed thousands or even millions of labeled images. And through backpropagation, it adjusts its filters and weights to become more accurate at recognizing those features and classifying the images correctly.
So practice makes perfect, even for neural networks. But I'm thinking, if a CNN is trained on, say, pictures of cats and dogs, how would it handle something completely different, like a car or a tree?
That's a great question. The key is in how the network is trained. If you want it to recognize a wider range of objects, you need to train it on a more diverse data set.
So it's like expanding its vocabulary of visual concepts.
Exactly. And that's one of the exciting areas of research in computer vision building CNNs that can recognize and understand a vast array of objects and scenes, just like humans can.
This is incredible. It's like we're giving machines the ability to see and interpret the world. But I'm also curious about the practical applications of CNNs. We mentioned facial recognition and self-driving cars, but what else are they being used for?
The applications are truly vast and growing all the time. In healthcare, CNNs are helping doctors analyze medical images like X-rays or MRIs to detect diseases earlier and with greater accuracy.
Wow.
They're also being used in security systems, robotics, even art analysis.
Wow, it seems like CNNs are becoming almost as versatile as transformers, but in the visual realm.
That's a great observation. And these are just two examples. There's a whole zoo of neural network architectures out there, each designed for specific tasks. We have recurrent neural networks, or RNNs, that are great for processing sequential data like time series or speech. And then there are generative adversarial networks, or GANs, which can generate incredibly realistic images, videos, even music.
Hold on, we need to unpack that last one. GANs. They can create things. That sounds like something straight out of science fiction.
It does, doesn't it? But it's real, and it's one of the most exciting and rapidly developing areas of AI research. Imagine two neural networks playing a game against each other.
Okay, I'm intrigued. How does this game work?
One network, the generator, tries to create fake data, say, an image of a person.
Okay.
The other network, the discriminator, tries to tell whether the image is real or fake.
So it's like a forger trying to fool an art expert.
That's a perfect analogy. And as they play this game, both networks get better and better. The generator becomes more skilled at creating realistic fakes, while the discriminator becomes more adept at spotting them.
Wow, so it's like an arms race of creativity and detection, constantly pushing each other to improve. But what's the point of all this? What can we do with these incredibly realistic fakes?
The applications are vast. GANs can be used to generate realistic images for video games, movies, or virtual reality experiences. They can also be used to create synthetic data for training other AI models, or even to restore damaged images or videos.
This is blowing my mind. It seems like every time we delve deeper into neural networks, we uncover another layer of complexity and possibility.
And we've only just begun to scratch the surface. There's so much more to explore, from the ethical implications of these technologies to the philosophical questions they raise about the nature of intelligence itself.
I'm starting to feel like we need a whole series of deep dives just to cover it all. But for now, I'm curious about the specific applications you found in the materials I sent you. What caught your eye? Okay, back for more neural network adventures. I'm ready to see how all this connects to the specific stuff I sent you. What stood out from those sources?
Well, given our conversation about the different network types, there's a fascinating example in one of the articles about how even a smart system can sometimes learn the wrong thing.
Oh, I love stories about AI gone wrong. What happened?
So researchers were training a network to distinguish between pictures of bears and dogs. A seemingly simple task, right?
Yeah, you'd think so. What could go wrong?
Well, the network seemed to be doing great, classifying most images correctly. But then, the researchers dug deeper into how it was making its decisions.
Hold on, we can actually see how these networks think. That's kind of creepy, but also cool.
It is. And what they found was surprising. The network had latched onto a pattern that wasn't about the animals at all. It turns out most of the bear pictures had snowy backgrounds, while the dog pictures were mostly on grass.
So instead of learning to recognize bears and dogs, it became a snow versus grass detector. That's hilarious.
It is funny, but it also highlights a key point. These networks are powerful pattern finders, but those patterns aren't always meaningful. We have to be careful about how we interpret their output.
Makes sense. It's a good reminder that even with all this advanced tech, human judgment is still crucial. Any other examples that illustrate this idea?
Another article you shared delves into the YouTube search algorithm, which, as you know, is powered by neural networks.
Oh, yeah. YouTube's recommendations can be eerily good, or sometimes like, send me down a rabbit hole of bizarre content. How does it work?
The algorithm analyzes your viewing history, your searches, even how you interact with videos to build a model of what you like.
So it's like a personalized TV channel constantly adapting to my tastes.
That's a good way to think about it. But there's a tension there, right? On one hand, it's great to have content tailored to you, but it also raises questions about whether we're being limited, only exposed to things the algorithm thinks we'll like.
That's a thought-provoking point. Are we sacrificing, like, serendipity, the joy of stumbling upon something unexpected in this quest for hyper-personalization?
It's a valid concern, and it's one of the broader themes that emerge from the sources you provided, the impact of neural networks on our information landscape.
That's a great segue. I did notice several articles discussing the potential societal impacts, both positive and negative. What were some of the key takeaways?
Well, one recurring theme is the potential for bias in algorithms, something we touched upon earlier with that bear and dog example.
Right, because if the data used to train these networks is biased, the output will be biased too. It's like a garbage in, garbage out scenario.
Exactly. And this has real-world consequences, especially when algorithms are used to make decisions about things like loan approvals or job applications.
So it's not just about making sure these systems are technically sophisticated. It's about ensuring they're fair and equitable as well.
That's a crucial point. And another big concern is the potential impact on jobs. As these systems become more capable, will they automate away tasks that humans currently do?
Yeah, that's the classic fear around automation, isn't it? Robots taking our jobs. But I've also read arguments that AI could create new jobs, or at least change the nature of existing ones.
You're right, it's not a simple equation. Some jobs will undoubtedly be impacted, but new opportunities will emerge, particularly in areas related to developing, managing, and maintaining these AI systems.
It seems like adaptability and lifelong learning will be more important than ever in this evolving landscape.
Absolutely. And alongside the practical implications, there's a whole philosophical layer to this conversation as well. As these systems become more complex, we're forced to ask questions about the nature of intelligence itself.
Wow, that's getting deep. Are we talking about like whether machines can truly think?
Exactly. Some experts argue that even the most sophisticated AI systems are still just mimicking human intelligence, not truly understanding the world the way we do. Others believe we're on a path towards artificial general intelligence, machines that can think and reason as well as or even better than humans.
That's both fascinating and a bit unsettling. It seems like this deep dive has opened up more questions than it's answered.
That's often the case with exploring cutting-edge technologies. It's a journey of discovery, not just of the technology itself, but also of its implications for ourselves, our society, and our future.
I'm definitely feeling that sense of wonder and a little bit of healthy anxiety. But that's what makes this so compelling, right? It's not just about bits and algorithms, it's about what it means to be human in an increasingly technological world.
Well said. And the more we understand about these technologies, the better equipped we'll be to navigate this complex landscape and shape it in ways that benefit humanity.
That's a great note to end on. This has been an incredible deep dive. I feel like I've gained a much deeper understanding of neural networks, both the technical details and the bigger picture implications.
It's been a pleasure exploring this fascinating field with you. And to our listeners, thank you for joining us on this intellectual adventure. We hope it sparked your curiosity and inspired you to continue learning about this transformative technology.
Until next time, keep those neural networks firing.